Okay, main part for today is the calculation of the source table. So with the analysis of variance, as we know, we're partitioning the variance in our study into basically two pieces, what's referred to as treatment or between groups, or error within groups. Okay, so we're going to partition that variability, and what we're going to come up with is what's referred to as a source table. I'll talk about that. And once again, HO, the three population means are identical. And H1, HO not true. Don't have to overcomplicate it. Just simply saying HO not true is good enough. Okay, as we talked about, I'm partitioning the total variability of the study into two pieces, that which is within groups, which is the error within our groups, or I'll refer to it as our within groups variability, which there's within groups variability for the undergrads, within groups variability for the college students, and within groups variability for the grad students. There's also between groups variability. The three groups differ from each other. The mean for the undergrads was 20, the mean for the college was 25, and then the mean for the graduates was 30. Okay, so we're going to see, are the groups fairly spread apart, and is the amount of spread, that is how far apart the groups are, is the variability due to that greater than the variability that is within each of the groups? Now we're just going to walk through the calculations and a bit of the logic. Okay, as we said before, prior to treatment, in this case it would be prior to their education experience, there's the general population mean, and there's variability within the population, and that kind of like normal distribution of individuals across the population. The variability is referred to as error term, right? So that's in terms of people's scores overall the general population on our Likert scale on perceptions of government. In our group, the treatment really, or within groups, the treatment is their education experience. Have they experienced graduate school education? Have they experienced undergrad? Have they experienced college? And I'll say it's distinct. So they're distinctly three different groups, right? So the college students have never done a completed university, undergrad. Well, they're not they can't be because the graduate students have completed undergrad. Okay, but you know what I'm getting at. So with the alternate hypothesis, what I'm driving at is after treatment or after experience, the grad students, there's an influence on the distribution of scores in the population driven by being a grad student. There's a separate, distinct level of influence from being a college student and also being an undergrad. This is my between groups variability. This is my within groups variability. Okay. Now, okay, let's just keep going. Okay. So, in terms of variability, in terms of our source table, we're going to walk through the calculations for the source table. So I have the source table here. The total sum of squares is 952. And that total sum of squares is this calculation right here. M here is referred to as the grand mean. So I'll walk through that in a bit. And the grand mean is the overall mean for the 27 individuals. I take each individual score, irrespective of what group they're from. I take their score and I subtract from it what we call the grand mean, which if I tally the scores for all 27 people, irrespective of what group they're in, tally those scores and divide by 27, that will give me the grand mean. So SS total, sum of squares total, is made up of each individual score minus the grand mean for the whole study squared. Sum it all up. Now, I'm introducing here the double summation sign. And the double summation sign is kind of like the hands of a clock. Because when you're in summation, you're running a tally. So the N is kind of would be like the minutes hand of a clock, and the second here, the K, is like the hour. So we click to 1 o'clock, which is group 1, and then we go through all 9 subjects, or we go through all 60 minutes of an hour. Once we've gone through all 9 subjects and taken, say, for that group 1, and we've taken each person in group 1, taken their score on the scale, subtracted the grand mean, squared it. I do that for all 9 people in group 1. Once I get to the end, I reset, and then I click the K, which is kind of like the hour, to 2. And then I go through all 9 people and students in the second group. Once I go through all 9, I click again to 3 and then go through all 9. So you can see how it's kind of like analogous to the hands on the clock. You know, in hands on the clock, I'm at 1 o'clock. I go through all 60 minutes. I click to 2 o'clock. Go through all 60 minutes. Click to 3 o'clock. I'm thinking analog clock too. Well, I guess you can think digital. It doesn't really matter. Okay. So let's look at that calculation. So here is all 27 students. Called my 9 college, my 9 undergrad, my 9 undergrad. Here are their scores. I sum up all 27 scores. It sums up to 675. I divide it by the number of students, which is 27, which is I have 9 students in each of 3 groups. 9 times 3 is 27. The grand mean for my study is 25, right? So then what I do is, kind of like for each of these groups, each individual, I take their score on the perception of government scale, subtract the grand mean of 25, in this case 30 minus 25, and then I square it. So 30 minus 25 is 5, square it, 25. I do that for all 27 people or students. That gives me a sum of squares total of 952. Okay. Okay, so now this gets a little tricky. I have what's referred to as my between groups sum of squares. So my SS between treatments, or I should be, I'm going to be switching between treatments and between groups. So they're synonymous, and you'll see both. Okay, so my between treatments is their school experience, grad, undergrad, college. What I do is I take K refers to the group membership. So I probably should have done that here. So K is group, I did actually. K is group membership, N is the number of the individual number in the each respective group, 1 through 9. So I take the mean for each group minus the grand mean for the whole study, square it, multiply it by the number of students in the group. So in the first one for the undergrad students, it's 20 minus 25, which is equal to minus 5. Minus 5 squared is 25. 25 times by 9 is 225. I then do it for the college students. The college students, the mean for the college students is 25 minus the grand mean of 25. Square it, and then multiply it by 9. In this case, it's 25 minus 25 squared is 0. Then finally, I take the grad students, 30 minus 25, which is 5, square it, which is 25, multiply it by the 9 students in the group, and that gives me 225. So I sum the between treatments, or between groups, sum of squares for the undergrad, college, and grad. So the sum of squares between groups or between treatments, once again, those terms are used synonymously here, is 450. Okay. And we'll walk through the spreadsheet. We'll walk through some of the calculations here. Okay. Then the final sum of squares is my within treatment sum of squares. So for this one, once again, I'm rolling through all 9 individuals of a group, and then I'm clicking to the next group. But the sum of squares within treatments, I have an MK here, M underscore K. M is the mean for the kth group. I have 3 groups. So if I look at this as K being 1 being the, I'm doing it as a college students here. I flip around a bit. So the mean for the college students is 25. I have NK here. I take each student in the college group and subtract from that student's score on the scale. I subtract the mean of 25 for that specific group. Square it, and then continue on and do that for all 9 people. I then click to the second group, which I'm calling here the university grad students. So their mean was 30. So I take each student's score on the scale, subtract it from the mean for that group that they're a member of, which in this case is 30, So 30 minus 30 for the first person is 0. 0 squared is 0. Then for the final group, which is the university undergrad, I've got them here. I take each person's score and subtract from it the mean for that group, which is mean in this case K3. So 15 minus the 20 is minus 5. Minus 5 squared is 25. So what I then do is once I've got these square deviations from the mean for all 9 students here, all 9 students for the grad, and then all 9 students for the undergrad, once I have that, I sum up all those values, and it sums up to 502. Okay. So the key thing here is that what you're doing with analysis of variance is you're taking your sum of squares total, which is the 952, and you're partitioning it into 2 parts. The first part is the between treatments or between groups sum of squares, which is the 502. That's the second one we did after we did the total. Plus the within treatments or within groups sum of squares, which is 450. These are 2 additive components. The key thing here is that the total sum of squares is basically the sum of the between groups, between treatments sum of squares, plus the within groups or within treatments sum of squares. So 502 plus 450 is 952. So what analysis of variance is, in essence, is the partitioning of the total sum of squares into the piece that's due to the between treatments and the piece that is due to the within treatments. So the sum of squares between treatments plus the sum of squares within treatments adds up to the sum of squares total. And that will always be the case in analysis of variance. So in an analysis of variance source table, SS total is made up of SS between treatments plus SS within treatments. So once again, analysis of variance is basically partitioning of sums of squares. Okay. Recall that the variance is a measure of dispersion. And when we have a population, the variance is the average of the squared deviations from the mean, right? So if we had a population, we take the sum of squared deviations and divide by n. So really what a variance is, if we're thinking in the context of a population, it's equal to the average of the squared deviations from the mean. Or we can think of it as being the mean of the squared deviations from the mean. It's kind of a bit of a tongue twister. So if I look at it, the variance in general form, as I said, is the sum of the squared deviations from the mean divided, if it's a sample, by n minus 1. Right? So we have the adjustment factor for the n minus 1 because of the sample standard deviation is a biased estimate of the true population standard deviation. Now the ANOVA, the total variance in the study, which is the mean squared total. Now the problem with analysis of variance is they don't refer to the variance as variance. They refer to it as the mean square. Why? I don't know. You'll have to talk to Ronald Fisher about that. But you can't talk to him because he's been dead for a long time. Okay, so the mean square total or the total variance is that sum of squares total that we did back here, this one here. Take that sum of squares and divide it by the degrees of freedom. Right? So if I look at in general form, a variance in terms of the sample variance is basically the sum of the squared deviations from the mean divided by the degrees of freedom, which is n minus 1 if we think of it in the context of the t-test. So what we have to do now is calculate for our 3 pieces our total sum of squares. We need to calculate the degrees of freedom to figure out what the variance for the total is. We need to do the same for the between treatments or between groups to figure out the degrees of freedom, be able to calculate the variance that's between treatments. And we also have to figure out the degrees of freedom for within treatments or within groups to figure out that variance. So basically creating 3 variances. Okay, so the degrees, now we're dealing with here with sum of squares, right? So SS total is just referred to as the sum of squares, which we did a couple slides back. The degrees of freedom for the total study is the number of groups, and little n always refers to the number of people within a respective group, right? So our little n is 9. I have 9 college, 9 undergrad, 9 grad. So 9 times by 3 is 27. 27 minus 1 is 26. So for my total variance for the study, which I would, if I were to calculate this, just as a variance for 27, scores, I would take the sum of squares divided by what would essentially be n minus 1, over, which would be the 27 minus 1 is 26. But in analysis of variance nomenclature, it's little n, the number of people in each group, which is 9, multiplied by the number of groups I have, which is 3. 9 times 3 is 27. 27 minus 1 is 26. Okay. The between groups degrees of freedom is easy, because in the between groups I have 3 means. So the degrees of freedom between groups is k minus 1. K refers to the number of groups. So 3 minus 1 is 2. Okay, then the final degrees of freedom is the degrees of freedom for the within groups. I have 3 groups, right? So if I kind of like go back, if I look at it, I've got, let's go right back to here. I got 9 college students. So if I were to calculate the variance for those 9 college students, it would be, the degrees of freedom would be 9 minus 1 is 8. The degrees of freedom for the university grad students in isolation is 9 minus 1 is 8. The degrees of freedom for the undergrads is 9 minus 1 is 8. So I have 8, and 9 minus 1, 8, 9 minus 1, 8, 9 minus 1, 8. So I got 8 degrees of freedom here for the college, 8 degrees of freedom for the grads, and then 8 degrees of freedom for the undergrads. So basically your within groups or within treatments degrees of freedom is n, or k times by n minus 1. There it is. So the mean square within groups is the degrees of freedom within each of the groups. I have 9 students in each group, so n minus 1 is 9 minus 1 is 8. I have 3 groups, so 8 times by 3 is 24. And there's my degrees of freedom. So my degrees of freedom is 24 for the within groups or treatments. The degrees of freedom total was 26, and the between groups degrees of freedom was 2. So whereas my sum of squares were additive, 450 plus 502 adds up to 952. The same goes for my degrees of freedom. 2 for between groups plus the 24 within groups adds up to the total degrees of freedom 26. So in essence, what we're doing is we're calculating the partitioning the total degrees of freedom into 2 pieces. The between groups or treatments and the within groups or error within treatments. So 2 plus 24 equals 26, which is similar to what we did with the sum of squares. 450 plus 502 adds up to 952. So clearly what we're doing with analysis of variance, we're partitioning the total sum of squares and we're partitioning the total degrees of freedom. Okay, and there's our calculations. Okay, so what it ends up being is the analysis of variance is referred to as, in terms of the inferential test, is referred to as the, oh, sorry, I got to calculate my variance, right? So it's the variance is basically the sum of squares divided by the degrees of freedom, right? So it's a general form. So 450 divided by 2 is 225. 502 divided by 24 is 20.9. I don't calculate the total total variance because the analysis of variance is referred to as the F ratio. So it's F, Ronald Fisher, Fisher F. So the analysis of variance, the inferential score that I get in terms of my inferential test is called is F, F observed. And what F observed is, and it's also referred to as the F ratio. And what it is what you want to know is how much bigger is the mean square between groups compared to the within groups or error. And that's a ratio. So in this case, if I calculate my F observed is 10.76. That means that my mean square treatment is 10.76 times larger than my error within groups mean square. So what that means is my mean square, my variance between groups is larger than my error variance by a factor of 10.76. Okay. So the final piece then is I have to look up my F critical, right? Because I want to, for my null hypothesis, what is my F critical? And that's for what's the F distribution. So in the table that we have, D1 is your numerator degrees of freedom. D2 is the denominator degrees of freedom, right? So it's an F ratio. This is my numerator. This is my denominator, right? 225 divided by 20.9. 2 and 24. My numerator, my denominator. D1, D2. I have my D1 degrees of freedom is 2. My D2 degrees of freedom, which is my error, is 24. So 2 and 24 degrees of freedom. My F critical is 3.4. Okay. Because F observed is greater than 3.42, 3.4, I reject the null hypothesis, right? So the rule is if my F observed is larger than my F critical, I reject the null hypothesis for alpha equal to 0.05. This is kind of like a thing. I think there's some conspiracy here, but that's Ronald Fisher in about 1920, and he has a vape pen. Try to explain that. Okay. So what we'll do is then we'll go through some calculation. We'll go through the practice of calculating this. We'll do it in Excel.